everyone, welcome to MSML. My name is Hannah Lawrence, and today I'll be talking about some of our work entitled Phase Retrieval with Holography and Untrained Priors, tackling the challenges of low-photon nanoscale imaging. This is work with my collaborators, David Barmherzig, Henry Lee, Michael Eickenberg, and our project lead, Marylou, Gabrié. So our guiding question in this endeavor was, how can we most practically apply modern machine learning for inverse problem techniques to experimentally realistic and valuable phase retrieval settings? And just to give you an idea of what we consider experimentally realistic, the first constraint is no data set. We don't expect a practitioner who's imaging a sample de novo to have access to enough related data to apply a supervised technique. We also need to be able to handle noisy data and lost data. And we want to be faithful to modern practical experimental setups. So how do you image nanoparticles in practice? Well, via coherent diffraction imaging, you can diffract X-ray beams, here shown in yellow, from a specimen, this little green guy, such as a virus, protein, or crystal, onto a beam-stopped CCD detector. And the beam stop here, shown as this black circle, is going to protect the detector, and that's actually going to prevent us from measuring any low frequencies. So mathematically, what's happening is that we have an n-by-n real-valued specimen. We're going to apply a doubly oversampled Fourier operator, which gives us a 2n by 2n complex image. And finally, we're going to take the squared magnitudes of that Fourier data. This is our data. And the goal is to invert this process, so to recover the n by n real-valued sample from only its Fourier magnitude data. And a really basic thing you can see is that trivial symmetries cannot be avoided. So for example, the Fourier magnitudes of any x and any translation of x are going to be the same. And here we show periodic translation, but of course in practice your image is going to be zero padded somewhat, and this is going to coincide for small translations with normal translation. Just a word of caution, so practical and theoretical phase retrieval differ. So here we're only going to be thinking about oversampled Fourier measurements with a complex phase ambiguity and some constant factor oversampling, and recovery algorithms such as HIO work well in practice but do not really enjoy great convergence guarantees. This is a contrast with theoretical results in which you normally have Gaussian measurements, some sort of upsampling by a log n factor, and sort of different algorithms which enjoy convergence guarantees. A basic result known as Hayes' theorem says that recovery is possible but ill-posed. So this says that 2 times oversampling, as shown in the previous diagram, is sufficient to recover a 2-dimensional image from its Fourier magnitudes up to the trivial symmetries, which include translation, also conjugate reflection, and scaling by unit vector. As I mentioned, the HIO, or hybrid input-output algorithm, is a popular iterative approach which alternates between updates in real and Fourier space, but its convergence to the correct solution is not guaranteed. And in fact, recent work suggests that phase retrieval is fundamentally ill-posed. You can construct non-trivially distinct signals with near indistinguishable Fourier magnitudes. And this is really bad news for a practitioner who's trying to recover a ground truth from data which is certainly going to be noisy. And the kind of experimental answer to this problem is holographic phase retrieval. And here you're going to use a known reference object to simplify reconstruction. So this is actually a completely different physical setup. So as before, we're going to diffract some sort of waves through a specimen, but next to it, we're going to place a known reference object. And these two, the unknown and the known objects, their diffractions are going to interfere in your measurements. And we can represent this as follows. So here in this upper panel, we have the specimen X in the top left. We have some spacing, and then we actually have a known reference object, which might be random valued at pixels, but the key thing is we know those values. All of these 0 quadrants are one way of formalizing this double oversampling, and don't need to worry too much about it. And then as before, we still have a beam stop to protect the detector, but we measure some sort of Fourier magnitudes coming from both the unknown specimen and the known reference. And one way that you can see that this is better is via this kind of simple commutative diagram. Holographic phase retrieval is well posed because when we take these Fourier magnitudes, what's happening in real space is we're computing the autocorrelation of this full image, which includes both X unknown and R known. And if X and R have this appropriate 0 spacing between them, what happens in the autocorrelation is that these linear parts shown in red, which are linear measurements of X, so X correlated with R, are separated from the other parts of the autocorrelation, which are nonlinear. And in fact, this becomes a linear inverse problem even if you restrict only to these red quadrants of the measurements. Just want to highlight that holographic separation condition one more time, which shows that in order for this to be a linear inverse problem, you do need some sort of sufficient separation between the specimen and the reference. or a slightly weaker version of that, you at least need for one pixel of the reference to be n pixels away from the unknown specimen in order to be able to extract a linear system. But it's very clear that once you have a linear system, this kind of solves the ill-conditioning issue for a reasonable choice of reference. So that's all well and good, but of course there are still practical challenges when you're working with real data, the first of which is noise. So we can let NP denote the expected number of photons per detector pixel, and of course we're not going to measure the true Fourier magnitudes, we're going to measure some measurements with Poisson shot noise where the rate is dependent on, of course, the true magnitudes as well as the number of photons. And for few photons, this is the high noise regime. Additive Gaussian noise is not a good approximation to this Poisson shot noise. As before, in addition, we have a beam stop, which includes low frequencies. And of course, you may have physical constraints that limit the types of references you can manufacture, as well as the separation from the specimen you can enforce. So our goal here is to leverage some of the work from machine learning for inverse problems to address these concerns in a very practical and promising setting, experimentally, such as holographic phase retrieval. And there's a wide variety of trained methods for solving inverse problems, some of the citations of which are listed here, and some of which have been applied to kind of toy data sets, but within the Fourier phase retrieval regime. However, for us, we're interested in untrained methods, and one that stands out in particular is the deep decoder architecture. So this is an untrained generative model, which has been applied for phase retrieval, but not in the holographic setting, and that's part of what we'll explore here. So the deep decoder is an untrained image prior, and what that means is that the architecture itself imposes an inductive bias favoring image statistics. This one in particular is a sequence of upsampling and convolution layers, and the way this works is you have some sort of fixed random input z, and as a result of all of these blocks of upsampling and convolution, and of course some nonlinearities, the idea is that by fixing these, picking the correct choice of convolution parameters, you can output hopefully any natural image. So this brings us to our primary method, which is Poisson maximum likelihood combined with the deep decoder. So as in any maximum likelihood setting, we're going to maximize the specimen X over the specimen X, the probability of observing the magnitude measurements that we have. And in particular, we can write this out on the second line here for the case of the Poisson distribution on our measurements Y, and we're going to ignore any pixels which we don't measure due to the beam stop. And it's as simple as that. To include the deep decoder, we're going to restrict the maximization to specimens X, which are in the range of the deep decoder. So hopefully this will restrict us to only looking at natural images, and we will naturally optimize this very non-convex objective using automatic differentiation in PyTorch. So what's some intuition for what we're doing here? So unlike the linear approaches, which are based only on these red sections of our measurements, X correlate with R, where we know R, we're also implicitly leveraging the nonlinear part of the data. In addition, the deep decoder is further restricting our search space, and hopefully the combination of these can compensate for some of the missing data or the challenging aspects of experimental data and enable reconstruction that competing methods cannot. So we actually test this, of course, and we're going to use 3 small data sets, and note that we're not training anything on these data sets, we're purely using them for evaluation. And we use a collection of image processing images, set 12, a collection of biological specimens, which is bio 10, and coil 100. And one thing to note about the coil 100 image which are objects on 0 backgrounds, is that perhaps these may be, in some sense, the most realistic because the object support lies strictly within the window, the 128 by 28 image. So as our metric, we use the structural similarity index, which is a better metric for measuring image similarity than just L2 norm. We compare to 3 baselines, and actually there's no machine learning baseline that we could think to compare to, but we do compare to some classic baselines. So first we use a custom variant of HIO, which enforces the known reference in its real space iterations. And we also use inverse and Wiener filtering, which are both deconvolution methods, the latter of which is under a Gaussian noise assumption. And as a sort of way of seeing exactly how much the different facets of our method improve reconstruction, kind of like an ablation study, we do test a few variants. So you'll see in the plots, an S denotes the squared loss, a P the Poisson loss, TV indicates that we add a total variation regularization term, and DD indicates that we're using the deep decoder prior to restrict the search space in the maximum likelihood optimization. And when that's not present, we're optimizing over the full space of n by n pixel images. So for our first experiment, we're simply looking at reconstruction at different noise levels, and this is one particular image, although of course we tested on the full data set. And I just want to point out a few things. First, at low noise, i.e. high number of photons, all of the methods do relatively well, both baselines and our methods, which we would probably expect because that's an easier setting. But at a low number of pixels, which is a high noise setting, we see that our methods in these rightmost columns obtain much cleaner reconstructions than HIO, inverse filtering, and Wiener filtering. So that's quite encouraging. That's what we're hoping for. Another thing I want to point out is that the squared loss is essentially worse than the Poisson loss in all settings. So Poisson loss always performs at least as well as the squared loss, which we would hope because that is actually the physical generating process, although we're simulating it here. And we also note that the squared loss sometimes leads to artifacts in the images that are reconstructed when in conjunction with the deep decoder. And we can see these trends repeated on this virus image and also in the coil image. And note that also in some cases the TV regularization is going to sort of smooth out fine-grained details. Of course, we can quantify all of this with the reconstruction scores, the SSIM as well. Broadly speaking, what we see is that the Poisson loss is strictly better than the squared loss. The deep decoder is the most helpful in a high noise regime as a prior. And the relative performances between using the deep decoder and having total variation regularization is somewhat image dependent. So the deep decoder, you can of course go back and check this or look in the paper, but generally allows better contrast, while the TV regularization smooths out constant backgrounds, which is advantageous, but sometimes also erases details. So our expectation for a practitioner would be that one could try with and without the deep decoder and perhaps with and without some level of TV regularization and see what kind of yields the best reconstruction. Now we also test missing low frequency data via the beam stop. And the question we ask here is how big of a beam stop can we actually tolerate using the extra information of the deep decoder and the nonlinear parts of the measurements? So here we're testing a variety of beam stop sizes varying along the columns, and we're comparing to all three of our baselines. And we see that our methods actually, this is perhaps the most drastic experiment. So for example, consider this column with a 1e-3 area fraction of the beam stop. We're getting much better reconstruction using our methods Holopt-P and Holopt-P-DD, the latter of which has the deep decoder, whereas HIO and inverse filtering barely get anything recognizable, and Wiener filtering has some sort of a phantom, but it's really not comparable. Of course, for a large enough beam stop, all of the methods fail. There's just too much missing data to compensate for. But we see that our methods are really able to push the size of a beam stop that still enables passable reconstruction. And this is verified by the SSIM, which is averaged over the entire data set. Another setting we test is actually breaking the holographic separation conditions. So we eliminate this zero spacing between X and R, and we even use a very small reference, which we move closer and closer to the image. So we're breaking all manner of holographic separation conditions. Wiener and inverse filtering don't even apply here, which gives some sense of how challenging the setting is, but of course our method is quite general. Can automatically differentiate through any forward model with the Poisson maximum likelihood, and we can only compare to HIO. And we see that both of our methods do far better than HIO, which is the only possible baseline, and this is also verified by the SSIM. And finally, I'll just continue on to our final experiments for the sake of time. We test a lower sample complexity, which corresponds to reducing the oversampling rate, so sampling at a much lower density within the same frame of reference. And we're only considering, or we additionally consider oversampling ratios smaller than 2, so smaller than what Hayes' theorem would dictate. And again, we see that we're able to do this, and we're able to do it better than the baseline, confirmed numerically across the entire data set. And finally, we did manage to get our hands on a little bit of experimental data using a laser from Guizar, Siqueiros, and Phenop's data with a triangular reference, and we can compare all methods here, where the 3 baselines are on the left and our 4 variants of our method are on the right. And I think it's fair to say that especially when we use the deep decoder, even with or without TV regularization, we're getting the best reconstruction on real data out of all of the methods. So this is super encouraging. There are some idiosyncrasies, such as TV regularization does some extra smoothing, but broadly speaking, this is kind of experimental validation for our technique. So in conclusion, we can obtain state-of-the-art reconstruction in holographic phase retrieval by combining a deep decoder prior, Poisson maximum likelihood, and automatic differentiation. It's advantageous to harness the complete measurement and forward model, even if the resultant problem is nonlinear, and these untrained image priors, such as the deep decoder, are confirmed to be helpful in challenging experimental settings, such as noise, lost frequencies, and low oversampling. Thanks so much for listening. I'll just mention some acknowledgements, and references can be found in the slides. Thanks.